Alright, so this lesson is now about dependent events. We had independent events in the last one, and we have dependent events in this one. And before I go anywhere, I want to start with a formula, right? We already know that the probability of A intersect B is equal to the probability of A times the probability of B given that A has happened. And this is our dependent events formula. And on the one hand, like, we can just memorize that, okay, fine. But I think there's a really beautiful thing that we can see if we look at this in the light of a Venn diagram. So stay with me on this. What I'm going to do is I'm going to rearrange this formula to solve it for this. I'm going to say that the probability of B given A is equal to the probability of A intersect B over the probability of A. So bear with me for a minute. Let's take a look at this in a Venn diagram. Let's say that I have a Venn diagram here. And let's say that this circle represents event A, and this circle over here represents B. Right? So what if I first asked you to envision, what does the probability of A, like, what is that? The probability of A, like, geometrically, wouldn't that be the area of circle A over the area of everything? Right? Because that's what our sense of probability is, that it's A over the total possibilities. Right? That's what that is. Here's where it gets neat. Right? What if I asked you, what is the probability of B given A? Like, think about what that means to you. That should mean, okay, the probability of B given A. Given A means A happened. B given A means I'm inside that A circle. That is my everything. Right? Probability of A is like, that has already happened. Now that I'm inside of that region, where can B possibly happen? If I've restricted myself to being inside of A, for B to happen, it has to be right here. And geometrically, what is that region? That region is the probability of A and B. Right? That thing right there effectively gives us the formula that we said from the beginning. And so when I see these conditional probabilities, I see these things as what I call a restriction of the sample space. And what that means is I'm saying, hey, if they say what's the probability of B given A, it means look at where A happened first. Then within that, look at where B happened. And if you write that as a fraction, you will find the conditional probability. That's how we do these things, right? So sometimes we're going to use Venn diagrams, sometimes we're going to use tree charts, tree diagrams for these things, so I'm hoping I can give you some examples of both of those. So before I get into any Venn diagram or tree diagram examples, I did want to do sort of one simple example, right? So given that a number rolled on a six-sided die is even, what is the probability that it's a prime number, right? So I mentioned before that these given, and when you see the word given, like that, often that means that these things are going to be dependent probabilities. So given that a number rolled on a six-sided die is even, what's the probability that it's prime? So you sort of start off by saying, like, okay, well, a six-sided die, 1, 2, 3, 4, 5, 6. This is my sample space. And if you missed that in the reading earlier, the sample space just means what's possible. So this is my sample space. When it says given that a number rolled on a six-sided die is even, it means you are restricting your sample space. So I am restricting myself to only looking here, here, and here. The other things might as well not have happened. If I rolled the thing and I got a 5, well, that's not what I'm talking about here. Right? Given that it's even, so given that I'm in this category, what is the probability that it's prime? So, prime numbers, sure, there's a 3 here, that's prime, there's a 5 here, that's prime. Cool, don't care about those, because I am only looking at my restricted sample space of the 2, the 4, and the 6, right? So, mathematically, this question is saying, what is the probability of prime given even? Well, out of the 3 things that I'm looking at, only one of them is prime, and so we're looking at 1 out of 3. Okay. So when I talk about it being a restriction of the sample space, sometimes it's going to be a counting problem like this, where we see that kind of thing. So the example we had before this one was one we sort of took a conceptual route through. In this example, you'll notice you're just given a lot of sort of disjoint data. They just say, oh, this probability is this, you've got another probability, find a probability. A lot of times when you have problems like this, just sort of running at the formulas can be helpful. So the formula that we have that sort of relates the intersection and dependent events is the one that we mentioned at the beginning of this. The probability of A intersect B is equal to the probability of A times the probability of B given A. And we have to stop and sort of think here, like, is this formula helpful for us? Can we actually work with this? So we have A and we have B given A, which means we should be able to find this intersection, right? So if I just plug these numbers in, we should be able to find that the probability of A intersect B is equal to A, which is 0.6, and B given A, which is 0.5. Let's see here, this ends up being 0.3. So that's our answer for part A. Okay. Now for part B, alright, so that was A. For part B, they want us to find the probability of B. Well, at this point, we have A, we have the union, we have the intersection. At this point, we can probably use the probability of A union B is equal to the probability of A plus the probability of B minus the probability of the intersection. Right, so if I just plug in all the pieces that I have here, we've got 0.7 equals 0.6 plus, let's see here, B is what we wanted to find, minus the intersection, that's what we found before, that's 0.3. If I just solve these pieces a little bit, let's see here, we should find out that this is, so you've got 0.7 equals 0.3 plus the probability of B, means the probability of B happening is 0.4. Right? Now the last question, they ask us to show that A and B are not independent. And if you remember from the previous video, our test for independence is to look at whether, what is the probability of A times the probability of B? Right? Well, the probability of A was given earlier in the problem as, let's see, A was 0.6. So we have 0.6 times the probability of B, which is 0.4. I'm getting that to be 0.24. Notice that that is not the same as the 0.3 that we got up above. Because of that, we know these two events are not independent. Alright, so this example is probably the most important one that I have. And part of the reason it's important is I feel like this style of word problem is something that the IB exam asks a lot. This problem is going to lead to a tree diagram, and a lot of times the IB will give you sort of a framework. They'll give you a skeleton for that tree diagram, and you have to fill things in. So hopefully I can help you with that. Right? So you've got box A that has some marbles in it, box B also has some marbles in it, and then another event comes in. A standard die is thrown. If a 6 is obtained, you pull a marble from box A, and if a 6 is not obtained, then you pull a marble from box B. And so the way that they recommend you set up the tree diagram here is that first you start with the independent event, right? So green and red are not independent because notice there's a different probability depending on what box you pull out of, right? The thing that's independent is the die, right? When you throw the die, you are either going to get a 6 or you have the probability of not 6, right? The probability of getting a 6 we know is 1/6. The probability of getting not a 6 we know is 5/6. So sometimes on the IB exam they'll leave one of these blank or they'll leave both of them blank and you have to fill them in. Right? So now what happens, right? If you follow this path in the tree, right? If you go this way, you had a 1 in 6 chance of rolling a 6. If you roll a 6, what happens? If that happens, then we are in a position where we are drawing out of box A. Right? And box A has different possibilities, right? Up here, we have getting a green marble. And I want to be careful about labeling this. This is not the probability of green. This is the probability of green given that we pulled a 6. Right? And that probability is 3 out of 10. Because within box A, you have 3 out of the total of 10 marbles being green. Okay? Going down on this branch, right, again, labeling it carefully, this is the probability of red given 6. And that probability is 7 out of 10. Right, we have a very similar thing happening down here at the bottom. Right? Down here, if we roll not a 6, it means we're pulling out of box B. And these probabilities are different, right? You have a 6 out of 10 probability that is, and if you're up for it, take a second, pause the video, and think about how you would label this. Right? What would you label this as? This should be the probability of green given not 6. And then down this way, we're going to have 4 out of 10, which is the probability of red given not 6. Okay. Now, in case you didn't pick this up in the earlier lessons out of the book, what you now do is multiply on each end of this probability diagram. So up here at the very top, we have the probability of what? Of getting 6 and green. And that probability is 3 over 60. And I'm not going to simplify, I'm just going to leave it like that for ease of canceling later. This one here is the probability of 6 and red, which is 7 out of 60. Down here, we have the probability of, and actually, pause the video, make sure you can do this on your own. This is the probability of not 6 and green, which is, let's see here, 30 over 60. And then finally here, you have the probability of not 6 and red. And again, just multiplying. I'm multiplying the 5/6 and the 4/10. This is going to give me 20/60. Okay? Once you have this tree diagram done, the problem becomes a lot easier. Because now we're just answering questions. Question A says, what is the probability that the marble selected is green? So appropriately, we'll use green for this. In this tree diagram, this is actually kind of fun. If you look over here, if you add up all those things, 3 plus 7 plus 30 plus 20, you'll get 60. You'll get 60 out of 60. This is the everything that can happen. So over here on the far right, where did green happen? Right? We had green here, and we had green here. So what is the probability of getting a green from here or getting a green from here? Well, remember, when we have an or probability, part A of this thing, or probabilities, we tend to add them together. 3 out of 60 plus 30 out of 60. This is 33 out of 60. That is the probability of pulling out a green marble, period. Okay? Now, part B is where I really love these problems. It says, given that the ball selected was green, what is the probability that it came from box A? Now, if you remember from the previous video, what I said about given problems is that they're basically restrictions of the sample space. So when I say given that the ball selected was green, it means, hey, guess what? We are in the category of green selections. Now, of those two, when did it come out of box A? Box A was only this one, right? So, what is the probability that it came from box A? Well, our total sample space was 33 out of 60. Box A was 3 out of those 60, which means this is 3 out of 33, which you could reduce to 1 out of 11, but that's the idea. And I mean, if you want to see it, this came from the formula. This came from me saying, this was the probability of 6 and green divided by the probability of green. I really don't even see the formula when I do this. I see it as looking at the end results of the tree diagram over here, putting the favorable outcomes on the bottom, putting the restricted sample space on the bottom, and the favorable outcomes on the top. I know this is a long video. Probability is tough just because we've got to wrap our brains around it. So I hope that made sense, and we'll clear some things up in class if you still have questions.